Very good morning, ladies and gentlemen, and a warm welcome to the CCUS Technical Workshop Asia CCUS Network. And I am Dian Lutfiana, Energy Research Associate of ERIA, Economic Research Institute for ASEAN and East Asia, and I will be your MC for today's workshop. Briefly today about this technical workshop. In this occasion, you will hear insights from Mitsubishi Research Institute, Global CCS Institute, and Mitsubishi Heavy Engineering about technical aspect of carbon capture technology. Okay, without further ado, it is my great pleasure to invite Dr. Han Phoumin, Senior Energy Economist of Economic Research Institute of ASEAN and East Asia, to give his welcoming remark. Please, Dr. Han, floor is yours.
Very good morning. First of all, thank you so much, Dian, for the floor to me. Again, very good morning, members, supporting member of Asia CCUS Network, and distinguished participants, ladies and gentlemen. Today, I'm very pleased for the opportunity to make a brief opening remark for the first technical workshop on the technical aspect of carbon capture technologies. This technical workshop is one of the series of workshops that fall under the pillar of capacity building training of the major activity of Asia CCUS Network. That we aim to bridge the knowledge gap on the CCUS technologies and development, so that we believe that countries can build their technical capacity to support the CCUS policy development in their respective national and regional policies. Today, I'm very pleased to share with you the progress of Asia CCUS Network activity since it officially launched on the 22nd June 2021 by Professor Hidetoshi Nishimura, the President of Economic Research Institute for ASEAN and East Asia, jointly with Mr. Hiroshi Kachiyama, the Minister of Economy, Trade, Industry of Japan. Just to recall that at the launching event, we also received a warmly congratulatory remark from Honorable Minister from Brunei Darussalam, Cambodia, Indonesia, Laos, PDR, Philippines, Singapore, Thailand, Australia, and United States for the leadership of MITI and ERIA in setting up the Asia CCUS Network Forum, which aimed to serve as a platform for cooperation and collaboration on low-emission technology partnership that will hopefully eventually accelerate the deployment of CCUS to achieve the carbon neutrality in our region for the foreseeable futures. The Asia CCUS Network key activity that include promoting knowledge sharing through holding an annual forum, conference, workshop, and meeting. Also, we conduct research study on technical, economical, and legal standard of CCUS in EAS region, and also hold capacity building training workshop to break knowledge gap on CCUS. Thus, today's conference is one among other activities to contribute to the mission of the network and bridge the knowledge gap on the CCUS in Asia regions. We at the Asia CCUS Secretariat have successfully organized a series of CCUS knowledge sharing by inviting experts from key relevant institutions on CCUS to share their work and insight on the CCUS development and opportunity. Just to recall, at the first Asia CCUS Network Knowledge Sharing Conference, which happened on the 26th July, we had experts from the IEA, International Energy Agency, to share their knowledge and insight on the key finding of their recent publication on the CCUS, the opportunity in Southeast Asia. At the second Asia CCUS Network Knowledge Sharing Conference, we had also experts from the US DOE to share their knowledge and experience on US policy development in support to CCUS at various levels, especially the federal environmental law and policy that affect the CCUS development, the overall CCUS project in the United States, and their international policy engagement in support to the CCUS deployment. And we are going to have the third Asia CCUS Network Knowledge Sharing Conference to be held on the 14th October 2021 by having experts from OGCI to talk about the effort on climate mitigation and CO2 storage. On the CCUS capacity building activity, we will also have a series of workshops, and today is the first technical workshop focusing on the aspect of carbon capture technologies. We all know that the role of carbon capture, utilization, storage is very crucial in clean energy transition, as it is the only technology that contributes both to directly reducing emission in the identified highly energy and intensity economic sectors, and to removing CO2 to balance emission that cannot be avoided. However, the deployment of CCUS will need to have appropriate supporting policies and investment. Thus, in supporting development of CCUS policy, technical experts will need to understand the technical aspect of the CCS, and we hope that today's technical workshop will enhance the technical understanding of these CCUS technologies. I also wish to take this opportunity to thank the MRI, Mitsubishi Research Institute in particularly, for working hard with the ASEAN to host a series of technical workshops on CCUS. Particularly, I wish to thank Ms Kikuko Shinchi and their MRI team for their support and collaboration to make this workshop happen. And also on behalf of the Secretariat of Asia CCUS Network, I'm very thankful for today's speaker, Dr. David Kerns, Principal Consultant CCS Technology from GCCSI, and Mr. Takashi Kamijo, Chief Engineering Manager and Project Director, Decarbonization Business Department, Mitsubishi Research Institute, that they're going to deep dive into today's technical workshop. Last and not least, please visit our Asia CCUS website from time to time for our update activity. I stop here, and I hope you will find today's technical workshop very useful. Thank you so much. The floor back to you, Dian. Thank you.
Thank you, Dr. Phoumin, for your insightful and informative opening speech. Let's move on to the next agenda. So we will have Mrs. Kikuko Shinchi, Senior Researcher of Mitsubishi Research Institute, will give her presentation about introduction to capacity building and overview of CCUS business development in Asia. Mrs. Kikuko Shinchi, the floor is yours.
Thank you very much for your kind introduction. I just want to make sure if you can see my screen.
Yes, we can see it.
Great. Thank you. As I was just introduced, my name is Kikuko Shinchi. I'm Senior Researcher at Climate Change Solutions Group, a sustainable division of the Mitsubishi Research Institute. And I would like to introduce you to this capacity building and technical workshop and overview of CCUS business development in Asia, in particular to the topic of today's workshop, carbon capture. And first of all, I would like to extend a warm welcome to the audience as well as the participants of this workshop. And on behalf of Mitsubishi Research Institute, I would like to extend my gratitude for ERIA for entrusting the Mitsubishi Research Institute with assisting in organizing this workshop. As already mentioned by Dr. Han Phoumin of ERIA, the Asia CCUS network was launched in June this year, and at the forum, Professor Nishimura, the president of ERIA, said in his keynote speech that knowledge share and capacity building training workshops are crucial to bridge the knowledge gap on CCUS. And thus, we've organized this the series of workshops today. As mentioned already, there will be a total of 3 workshops covering the entire value chain of CCUS. The first day of the workshop is about carbon capture technology. The second day, we will touch upon the transport and storage technologies. And the third day, we will cover the technologies on utilization of CO2. Let me go through day one, which is today. We will feature lectures by two experts, Dr. Kearns, Principal Consultant of GCCSI, as already introduced by Dr. Han. And as many of you are aware, GCCSI is the leading global organization that promotes CCS with members from academic, public, and private sectors around the world. Dr. Kearns will lecture us based on his broad knowledge on CCS. On day two, we are happy to invite two lecturers on the topic of transportation and storage technologies. First speaker will be Mr. Ulysses Komas. He's my colleague and he has done considerable amount of research on business models around the world, and he will share with us his findings on the transportation technologies available and in planning today. And we will also have Dr. Shrey from Research Institute for Innovative Technologies for the Earth. He has also very long experience in researching storage technologies for CCS, and he will share with us his expertise. And on third day, we will cover the topic of utilizing CO2, which is a very exciting topic as it's related to new technology development and industrial application. And we have two speakers from the ASEAN region. The first speaker is from Pertamina, Indonesia. Ms. Midistarini will share with us the up-to-date information on the technology development activities of Pertamina. And also we will have Professor Ning Yang, assistant professor from National University of Singapore. National University of Singapore is also engaged in very exciting research activities in the area of CO2 utilization. And he will also update us on the latest technology development and also some application for industries in the ASEAN region. I would also like to introduce you to some of the background information on CCUS in the Southeast Asia region. As IEA estimates, to meet Paris Agreement goals, CO2 capture in Southeast Asia needs to grow considerably compared to what's being done today. The IEA estimates that based on a sustainable development scenario, which is in line with Paris Agreement goals, the carbon capture amount needs to reach about 35 megatons in 2030 and almost 200 in 2050, which is a very large volume CO2 that need to be captured, and we need the actions are required now. And CCUS is especially important in Southeast Asia region because as you all know, energy demand is continuously growing, and much of the energy demand growth is based on fossil fuel. And emissions from fossil fuel consumption and fossil fuel supply need to be addressed, as even considering the increasing amount of renewable energy input into the power supply in the region, fossil fuel will not go away for a considerable amount of time, and emissions from these fossil fuel use need to be addressed to combat climate change. And as you can see in the graph here, the energy demand growth in Southeast Asia is very high. It's just after China. And for potential solutions in introducing CCUS, IEA has proposed three main solutions. And one is the integration with zero emission power, with basically providing CCS retrofit for existing fossil fuel power plants to provide flexibility for renewable dominated grid. As many of you are aware, the more the renewable energy is introduced to the grid, the more flexibility is needed from other sources, such as the fossil fuel power plant using natural gas. So the importance of fossil fuel power plant with CCS is expected to grow in the grid to coexist with renewable energy. And also, as obviously, heavy industries will continue to depend on fossil fuels such as cement, steel, and chemical sectors. And providing CCS to these sectors is crucial. And also, a number of ASEAN countries has a crucial position in the natural gas supply chain, and capturing CO2 from gas reservoirs as well as gas turbines in these areas is also important. And the cost for CCUS is higher, but still comparatively to other options such as using hydrogen as alternative fuel is still lower. And I would just also like to give a brief overview of various CCUS technologies available today. They're at the varying maturity stage in terms of technology development. And I'm very happy that we have two speakers with expertise in the carbon capture area. So they will, I'm looking forward to hearing their lectures so we can learn the technical contents of each technology, as well as advantages, disadvantages, and what they can, how they can be applied to Southeast Asian context. Thank you very much. I would like to conclude my presentation here and hand over to my, back to the MC from ERIA. Thank you.
Thank you very much, Mrs. Shinchi, for your introduction speeches and explaining how crucial CCUS development and deployment to address climate change issue as well as part of the pathway to carbon neutrality. In proceeding to the next session, we will have a presentation of overview of carbon capture technologies, its advantages and disadvantages by Dr. David Kearns, Principal Consultant of CCS Technology from Global CCS Institute. Without further ado, Dr. David Kearns, the floor is yours.
Thank you very much for that introduction. Appreciate that. As I said, I'm David Kearns. I'm Principal Consultant in CCS Technology with the Global CCS Institute. I'd like to just give you a little bit of a rundown for starters on the Institute and what it's about. So the Global CCS Institute is an international think tank dedicated to advocating on behalf of CCS as one of the solutions to our greenhouse gas emissions problem and as a solution to climate change. The purpose of today's presentation is really to give an overview of CCS technologies as they stand at the moment, as well as a comparison of the relative advantages and disadvantages of different types of CCS technology, of capture technology rather. I will just step through, there we go. I'll just step you through briefly. Some of this will be familiar to some of you, but really to set the scene and give context for the discussion. First thing I wanted to talk about were the different types of configurations that we see for carbon capture. If you have conventional combustion, it typically produces CO2 diluted mostly with nitrogen. So we combust fuels in air, air is mostly nitrogen, and so we end up with this dilute CO2. Carbon capture is all about separating out that CO2 with a reasonably high purity. Typically, we're looking for at least 95% purity by volume. And there's three sort of main ways that carbon capture is organized or arranged around combustion processes. The first is probably the one that people would immediately think of, post-combustion CO2 capture. That's an approach where we're separating the CO2 from the nitrogen after a conventional combustion process. So the example we've got here on the left is we've got a boiler, it's combusting fuel and air, it's producing an exhaust gas. Depending on the fuel, that exhaust gas CO2 concentration could be as low as 3 or 4% if it was burning natural gas, up to the order of 13, 14, maybe even 15% if it was burning coal. And then we go into our capture plant, which separates out that CO2 at high purity. The second approach is known as pre-combustion capture. Pre-combustion capture takes a different approach. It removes carbon from the fuel itself before combustion, hence the name pre-combustion capture. In this instance that's shown here, there's something known as an ASU, an air separation unit, to produce purified oxygen. That's used in a gasifier with the fuel. to produce something known as syngas. Syngas is a mixture of hydrogen, carbon monoxide, and carbon dioxide. We have what's called a shift reactor, which creates some more hydrogen from the carbon monoxide. And then finally, we do a capture step where we separate out the CO2 from that gas mixture. Effectively, what we're burning in the end is clean hydrogen. So the hydrogen has had the carbon removed from the fuel. That's a second approach. The third approach is known as oxy-fuel combustion. Oxy-fuel combustion says, well, since we have a mixture of nitrogen and oxygen, if we separate out the nitrogen before combustion, we have the opportunity to produce quite pure CO2 as a result of that combustion. So we again have an air separation unit. It separates oxygen out from the atmosphere, and we combust our fuel in some combustion process with that purified oxygen. Now, there's an important aspect to oxy-fuel combustion is that you need to recycle some of that CO2 that you produce. The reason for this is if you try to combust fuel with high purity oxygen, the temperatures can become so high that they will actually destroy or melt the materials of construction of your combustion system. So we recirculate some CO2 in order to cool down and keep the temperatures under control. So 3 different approaches, 3 different configurations, the end result being that you get combustion, you get heat, and you have a separate CO2 stream out at the end. So that's combustion processes, but that's not the end of the story. There's also industrial configurations. So a classic one, and in fact, a very widely deployed one globally at the moment, is in natural gas processing. So raw natural gas, as it comes out of the ground, often contains quite a bit of CO2 mixed up with the methane that we want. And those facilities already have what are known as acid gas removal units. So acid gas removal is removing CO2 and sulfur compounds, typically hydrogen sulfide. The nice thing about natural gas capture is that this step is being done anyway in most of these natural gas processing plants. CO2 has to be removed as a matter of course in processing natural gas. And therefore CCS is easier in this case because a lot of the hard work has already been done. It's more a matter of compression, dehydration, transport and storage of the CO2, given that the capture's already been done. Another example is cement production. So cement is the production of calcium oxide, Portland cement. We produce that from a raw meal, which is typically a calcium carbonate material or some other carbonate material. We heat it and that releases CO2. So this is not a combustion reaction. This is CO2 as a fundamental chemical reaction occurring when we make cement. That CO2 is unavoidable. So even if we switched the heat source in cement production to a fully renewable source like biomass, we would still produce quite a lot of CO2, typically the order of 50 to 60% of the CO2 produced in cement plants comes from the actual reaction itself. And so there's a need for CCS in that particular industry to handle that CO2 and give it an opportunity to be abated. And then something that's a little bit more recent, but I think is going to have a big future, is known as direct air capture of CO2. So as the name suggests, this is removal of CO2 directly from atmospheric air, so not from industrial point sources. The concept is pretty simple. You take air. Air is typically in the order of 400 parts per million, so very dilute compared to CO2 that you would find in most other point sources. You pump plenty of air through the plant and you reject air that's depleted with some of that CO2. The capture fractions are typically not huge because it's already very dilute as it is. And I've got a couple of examples there in the pictures. One is of the recently commissioned Climeworks Orca plant in Iceland. That's a relatively small plant by CCS standards, only 4,000 tonnes per year. But as it stands, that's the largest operational direct air capture plant in the world. But coming down the line is Carbon Engineering's direct air capture process. They've got their first project in development with Oxy in the United States. And that's intended to be a 1 million tonne per year CO2 capture plant. So that's 1 million tonnes of CO2 captured directly from the air. DAC is important because direct air capture is an opportunity for what's known as negative emissions. So it's not a reduction of emissions from some positive number to a smaller number. It's actually a negative number. There is a net reduction of CO2 in the atmosphere as a result of these processes. And in a world where we're looking to move towards net zero is going to require not only reducing emissions, but we are going to need some negative emissions to offset the remaining emissions that will be left even after we go for a deep decarbonisation. So technologies like direct air capture are going to become increasingly important over time. I'll take you through just the general categories of the technologies that are used. The most commonly used one is absorption or solvent-based CO2 capture. They deploy the use of a solvent that has a preferential absorption of CO2 from a gas into a liquid. So solvents are typically things like amines or potassium carbonate, some physical solvents like certain glycols. There's a range of other different solvent types that are coming along. And there's two different categories. There's the category known as chemical solvents, not only absorb CO2, but actually react it into other chemicals, into other species within the solvent itself. That gives it a lot more capacity to keep taking on CO2 and means you can actually get a lot of CO2 absorbed into each cubic meter of that solvent. There are also so-called physical solvents, which do absorb the CO2, but they don't react it away. So akin to how you would have CO2 in fizzy water or soft drinks. They tend to require higher operating pressures to work just because they have a lower affinity for CO2. You need more pressure to squeeze more CO2 into the solvent. And the diagram on the right there is a fairly high level but typical arrangement that you would have for a solvent-based plant. You have what's known as an absorber. An absorber is usually a packed column where the flue gas or the gas that contains the CO2 is emitted at the bottom and flows up. And simultaneously, we put our fresh solvent in at the top and it flows down over that packing, giving it lots of contact, lots of surface area to interact with that gas. It takes up the CO2. And then what we end up with is our clean flue gas coming out the top. That's had a substantial fraction of the CO2 that was in it removed. Typically 90%, although we've been seeing plenty of work and studies in recent times suggesting that getting to 99% removal of CO2 is definitely achievable. It's just a question of economics. The solvent that exits the bottom of the column is known as a rich solvent, and that's now containing a lot of that CO2 that we've removed from our flue gas. We need to then separate that CO2 back out so we can reuse the solvent. So it goes through a heat exchanger where it's warmed up. And that warmth that we add to the solvent, that helps to drive some of the CO2 back out of solution. So we end up with a reversal of that reaction that we had in the absorption step, and we're releasing CO2 back from the solvent. It flows down this desorption column. It's typically a much smaller column, and I'll show you a picture of an example in a moment. Goes down into a reboiler at the bottom, which boils or heats up some of that solvent and produces some more vapor, particularly a lot of CO2 vapor. And then at the bottom, we have a hot lean solvent. So that solvent has now been regenerated and is ready to use again. And then at the top, we just have a condenser that cools the situation down, refluxes a little bit of that fluid, and enables that to be processed and dealt with. One of the things about absorption systems is absorption systems are typically have a fairly substantial footprint. This is an example of an absorption-based system on a coal-fired power station in the United States. You can see here from the size of some of these vehicles down at the bottom that the equipment is physically quite large. And that's a reflection of the fact that they're typically dealing with substantial gas volumes. This facility was designed to capture 1.4 million tonnes of CO2 per year from a power station. And you can see there the height of this absorption column. This is the column that's taking this flue gas and taking up the CO2 is quite substantial. Whereas the desorber or the stripper column that regenerates the solvent, this one on the right, is physically much smaller. So that's absorption technology. There are many, many variants of this. So the flow sheet that I've shown you here is a very simplified flow sheet. There are lots of different configurations out there that involve different types of heat integration arrangements, in some cases multiple columns, different types of packing, and a big focus has been on the different types of solvents. So one of the challenges that needs to be dealt with are conventional amines like MEA and MDEA, which have been around for a very long time. They're very effective, but they do suffer from something known as solvent degradation. Over time, this repeated thermal cycling, this heating, cooling that we get, gives us an issue that some of the solvent starts to chemically break down and needs to be replaced. And so that's obviously an operational expense to have to replace those solvents. And so people have been looking for more advanced types of solvents or different types of solvents that can overcome these issues and are more robust over time. Next type of technology is known as adsorption, AD, not AB, adsorption-based CO2 capture. This is where we use a solid material as opposed to a liquid. It's typically a porous solid that preferentially takes up CO2 from a gas and adsorbs it onto the surface of that solid. There are two different approaches that have taken to running adsorption-based CO2 capture. One is known as temperature swing adsorption. The other is pressure swing adsorption. Temperature swing adsorption uses heat or temperature. We increase the temperature of that adsorbent and we drive the CO2 back off the solid into the gas phase. An example of TSA is this process at the bottom by Svante. It's their Veloxotherm temperature swing adsorption system consisting of 4 steps. There's the step 1 up here where there's a flue gas is put in contact with their adsorbent material. Their adsorbent material takes up some CO2 from the flue gas and the vent releases that treated flue gas to the atmosphere. And then we have a sequence of steps of a heating step where steam is used to heat up that adsorbent and help to release some CO2. They take some additional flue gas for recirculation and conditioning, and then they cool it back down with cold air ready to be used again. And they use this rotary bed arrangement where the whole physical apparatus turns around. And so this kind of arrangement is intended to enable you to capture fairly substantial amounts of CO2 in equipment that is physically smaller. The other arrangement for adsorption processes is known as pressure swing adsorption, which uses cycling between a high pressure and a low pressure to adsorb and desorb CO2. But the concept is somewhat similar. And then finally, we have membrane-based CO2 capture. So membranes are effectively very fine filters that can preferentially filter certain materials out of a gas stream. It's very similar technology to what's been seen in reverse osmosis that's used for desalinating seawater. There's an example picture there in the top corner of a membrane arrangement. Effectively, it's a bundle of individual hollow fibers of membranes. And they rely on the differential rates of mass transfer of CO2 and other gases across the wall of that membrane. In other words, CO2 will pass through more quickly than other gases will. And it means that the gas that passes through is more enriched in CO2. Membranes are usually quite sensitive to moisture, which is a point that I didn't mention earlier on. The absorption systems usually use an aqueous solvent, a water-based solvent. So water is kind of an inherent part of the process. In membranes, you actually need to dry the gas. So if you have a very wet flue gas that you're trying to capture from, then we do have to think about how do we dry that gas. And so at the bottom here, you can see they've used a water-based direct contact cooler followed by a molecular sieve. A molecular sieve is an adsorption-based dryer so that it's suitable to be deployed in the membranes. And you'll notice here that actually 2 membrane stages have been used. Typically, most membranes are not capable of producing very high purity CO2 in a single step. So if your feed gas was, say, 10% CO2, you might boost it up to 50, 60%, maybe 70% pure CO2 in the first stage. But taking you back to the start of my presentation, you actually need to be aiming for 95+% in most applications. And so there's typically a second stage needed. We take that enriched CO2 from the first stage, we recompress it, and we drive it through the second membrane stage to get our high purity CO2. One of the interesting things to note here is that the driver of that gas flow across that membrane wall is pressure. You need to have enough pressure of your gas that the CO2 will start to flow through the membrane wall. And so really the driver for membrane-based capture is compression. So that's just to give you a bit of an overview of what different types of configurations we have with our post-combustion, pre-combustion, oxy-fuel type arrangements, as well as our different types of technologies, so absorption, adsorption, and membranes. So there's a reason why we have different approaches to CO2 capture and why we might choose to use different approaches. So the first one is, if you look at a few different aspects of these technologies, one of them is the energy type that's used to drive the process. So CO2 capture, like any gas separation process, and indeed any separation process in any industry, must be supplied with an energy source in order to work. Mixtures of gases will not spontaneously separate into higher purity gas streams. You need to apply an external source of energy to drive that. And that's really just a consequence of the laws of thermodynamics. Certain technologies tend to be more suitable for different applications. So I've made mention here of which applications they're suitable for, and some other advantages and disadvantages that I'll step you through in a moment. So our solvent-based processes, the ones I showed you earlier, where there's sometimes a very large, physically large equipment, they're primarily driven by heat. They do use some electricity for things like pumps and solvent circulation, but the main energy consumption is heat, and it's typically fairly low-grade heat or moderate-grade heat, the order of 100 to 140 degrees, often provided as low to moderate pressure steam. So if you're in a location where that heat is abundant, then you're well set. Absorption are most suitable for high gas flow applications. It's not to say they can't be used at lower flow as well, but they have a distinct advantage when you start getting up to very high flows. Once you're getting up into the hundreds of thousands or the millions of tons per year, absorption really does have a significant advantage. And it has an advantage because of its capital cost advantage. The physical equipment is very large, but the scaling, the way that the capital cost tends to grow with scale, means you get economies of scale for that capital cost. Whereas for some of the other technologies, the economies of scale are not nearly as strong. Another advantage of absorption-based technologies is for the same flow sheet, you can actually have different types of solvent that you use. So I've mentioned before that we have different types of amines available. So MEA, MDEA, piperazine type approaches, proprietary amines as well. So different companies are out there patenting different solvent chemistries that are amine based. But there's also approaches based on potassium carbonate, including there's one company that's using enzymes to enhance potassium carbonate. And there's new technologies coming along as well that even follow other approaches than that. And so the fact that there's a range of different solvents out there means that different applications may actually be better or not so well suited for a particular solvent. So it gives you options. I mentioned earlier, one of the challenges that you have with absorption plants is the solvent degradation. So solvent degradation is something that we particularly see with the traditional solvents, the traditional amines, the MEAs and so on. Solvent degradation is a non-trivial cost to operating some of these plants. It is something you have to factor into your economics. And of course, you then have a spent solvent that needs to be treated. We can't just dispose of that into a sewer. We do have to actually chemically treat that stream. Usually that's done off-site. Another disadvantage of absorption is that the plants tend to be physically large. So that may not be a problem if you're in a location that's got an abundance of space. But if you're in a place where there is a real limitation of space, and I'll give you the example of people have been investigating capture of CO2 on ships, for example, absorption plants may start to struggle just to physically fit in that sort of environment. Adsorption plants in our second column there. Adsorption plants, as I said, are based on a solid material to drive the separation. They do have the advantage that you can choose to do TSA, temperature swing adsorption, which uses heat, or you can do pressure swing adsorption, which relies on gas pressure, usually provided via a compressor driven by electricity. And so depending on the relative cost of the energy available in your location, in some places heat may actually be cheaper, in other places electricity may be relatively cheaper. So that gives you different options there. If you're in a location where there's an abundance of low-cost renewable electricity, for example, you may want to look at pressure swing adsorption because it does give you that option of driving it electrically. Adsorption plants tend to have a cost advantage at low scale, so really quite small scale, moving up into the moderate gas flow ranges. And the reason for that is that one of the big costs of adsorption-based technology is the adsorbents themselves have to fill up these packed beds full of adsorbent. And the physically larger you make them, the costs of that scale linearly with the size of the bed, and the bed size tends to scale close to linearly with the flow capacity. So you don't get the same economies of scale for the capital cost in adsorption plants as you do for absorption plants. So they tend to have an advantage cost-wise at low and moderate scales, and then they start to fall behind the absorption technologies as you get to physically very large scale. They tend to have an advantage of being modular, and often they use quite non-toxic materials. One of the things I didn't mention earlier for absorption plants is absorption solvents sometimes are quite toxic. The materials are quite noxious. So amines, for example, you do not want people coming in contact with those. They're perfectly safe when they're locked away inside the absorption column, but you do have to make sure you've got good plant integrity. With adsorption plants, the solids that are used are often things like activated carbons or zeolite materials, which are porous aluminosilicates. These are benign materials that people can handle and are not going to cause any problems for humans. So that is an advantage for them. And as I mentioned, the costs do become quite high per tonne as you go to high flow rates, really because of this capital cost disadvantage. And the final one was membranes. Membranes are typically driven either from electricity to drive compressors, and in some processes, in particular in natural gas processing, where the gas stream is already at high pressure, you don't have to pressurize it, it comes out of a gas well at high pressure already. You can actually run off the gas's own pressure, at least in part. They tend to be suitable, again, usually for low to medium gas flows. You can run them for higher gas flows, but the capital costs can tend to get up there. One key advantage that membranes have is they have a small footprint. So they are much more compact for a given capacity than the other types. Indeed, we've seen one application of membranes for CO2 capture is in offshore gas processing. So Petrobras in their Santos offshore development off the coast of Brazil, they use membranes for CO2 capture because they're in an offshore environment where space is at a premium. They're prepared to pay more money for the capital cost of the membrane plant because it saves them having to build more platform space. And they also have a relatively light weight, so you don't have an issue with needing to support large amounts of physical weight. And again, these plants can be modular, which is a real advantage as well, particularly if you want to start with a plant that's a smaller scale and then add additional capacity later. That tends to work pretty well for membranes. One disadvantage for membranes is that they typically will produce the CO2 that they capture at a lower pressure. I mentioned before that CO2 goes through the membrane, and as it goes through that membrane wall, it loses pressure, which means you typically may need to compress it more as it comes through the membrane to the other side. So that pressure energy is being lost. And they also struggle for very, very high purity CO2. So the two-stage approach, which I mentioned on this slide here, of having a first membrane stage and second membrane stage, that could get you to 95% pure CO2, which is okay for pipeline transport. But if you wanted to liquefy your CO2, say to put on a ship, liquid CO2 typically needs to be even purer than that again, much closer to 99%. So membranes may even need a third stage if you wanted to go that pure. And a third stage would require an extra set of compressors and more energy consumption, which may lead you in that case to go to one of the other two technologies. And the final one is that it's not so suitable for low partial pressure CO2. So partial pressure is really an analogy for concentration. It's concentration times total gas pressure. Membranes really struggle when you get down to very dilute CO2 in your feed gas. They really just can't do it very well. To give you a bit of a context of how these projects are going, we are seeing in the Institute, we track the development of CCS projects globally through the life cycle, so early development all the way through to operation. This chart gives you an idea of what's been happening to that project pipeline over the past 11 years. We are about to release our global status of CCS report. It's coming out next week. And in that, I can't tell you the results of this year's numbers. That's embargoed until our report comes out. What I can tell you is that there has been strong growth in 2021. We've been seeing the order of 30% year-on-year growth in the capacity of the CCS project pipeline since 2017, and it's even been accelerating in 2020. So the growth is even stronger than it was in the last few years, particularly projects entering the early development. So I think the world's efforts to start moving towards net zero are focusing a lot of attention on getting projects started, particularly at early development, which is what we call feasibility, the feasibility level of project development. And then obviously that's going to lead to more advanced development and construction projects in the future. In terms of the facilities that these projects are being seen in, we're now seeing them across almost every application that you might care to point to that CCS may actually be used in. So we're seeing them now in cement. So the Norcem Brevik plant in Norway is the world's first CCS project in cement. That's now under construction. We see them in iron and steel in Abu Dhabi Steelworks. There's waste to energy applications, power generation of coal and gas types, hydrogen production. So producing hydrogen with CCS is known as blue hydrogen. And we're seeing it in chemicals, in ethanol production, fertilizers, natural gas processing. And now we're seeing projects operating in direct air capture as well. So it's really quite a diverse industry. It's not focused on any one sector. It's really sort of a varied industry that really works across a range of different sectors and is giving options for decarbonisation for a range of industrial and energy sectors all over the world, where we're really seeing deployment now globally, which is very, very exciting. And then finally, just a comment on cost. This is something that we often get questioned on for CCS. So this chart here is just to give you an idea of some of the relative cost ranges, indicative only. These are kind of benchmark type numbers. You should take these with a grain of salt for any particular project. But they give you an indication of the typical ranges of cost that you might see. On the y-axis here, we've got US dollars per tonne of CO2 captured. And on the x-axis, we've got different segments of the CCS value chain. So starting with CO2 capture, moving on to compression and dehydration, transport, injection and geological storage, and then ongoing monitoring and verification of that storage. And what you can see on the left in particular in the capture section is how much variation there can be in capture cost. So capture cost can be extremely low in the order of $1 to $3 US for applications like bioethanol. So making bioethanol produces CO2 from fermentation, which is effectively pure. It doesn't really need capture. It just needs piping and movement to a compression station. So the costs of that are extremely low. But then you start moving up to more less concentrated CO2 streams, like from steel blast furnaces or from coal generation. The costs tend to, as your concentration of CO2 gets more dilute, the costs of capture go up. And then up to the order of 4% that you might see in natural gas power generation or just natural gas combustion for heat purposes. The costs are higher because that CO2 is more dilute. And we've found that the key drivers that we see for capture plant costs are economies of scale is a big one. So larger facilities tend to have lower costs of capture per tonne than smaller facilities. The partial pressure of CO2, as I mentioned, the concentration of the CO2 times the overall gas pressure. If you've got a higher partial pressure, that tends to reduce the costs per tonne, which is what we've seen here on the left. We've got high partial pressure at the bottom here, moving up to lower partial pressure at the top. But then there's some other drivers as well. So there's the cost of energy. I mentioned that we're using heat or electricity typically to drive these processes. That's going to feed through directly to your operating costs. There's technology selection. So even within all of these bars, you will see different cost ranges for absorption or adsorption or membrane approaches, depending on the application. And then I think the final point to get across is that it's the full chain CCS costs that matter. Capture is not the whole story. And indeed, if you're in something like bioethanol, capture is in fact a trivial part of the overall value chain cost. Whereas if you're in natural gas processing, it's the dominant cost. So the industry actually and the CO2 application really does cause quite a distinct variation in the overall value chain cost. But it is important. So it's important to consider things like transport cost. You know, can you get access to good CO2 storage resources within a reasonable distance of where your capture is happening? You'll find that if it's a relatively modest flow of CO2 and you have to transport a long distance, those costs can suddenly become quite a bit higher. And the quality of your storage resource matters as well. So if you've got a good quality onshore storage resource with high permeability, that resource will be relatively low cost per ton. But if you have to go offshore, if the permeability is not as good, then the cost can go up significantly for storage. So this is one of the reasons why there's so much effort that goes into characterizing storage resources to try and make sure those costs come down. Just one final comment that I will make on the value chain is that we're seeing a real development, in particular over the last 18 months, of shared infrastructure, of sharing transport and storage infrastructure between projects. So historically, we tended to see vertically integrated developments where the capture, compression, transport and storage were all run by one entity and would really just be dedicated infrastructure for that one capture facility. Now we're seeing more of a deployment of networks around the world where transport and storage infrastructure is deployed at a larger scale to bring costs down and shared across multiple CO2 capture plants. That really does help drive improved economics. That was it from me. So I hope that was informative to all of you.
Thank you very much, Dr. Kearns. We have received some questions from the audience, which I hope you can shed some lights on. And okay, I will ask the first two questions first, then followed by the second two questions. First two questions. One is if direct air capture is prevailed all over the world, is there any possibility to break the CO2 balance in atmosphere? And the second question is on the utilization of aqueous ammonia for CO2 capture, if that's an available technology, and if it is, then the status of that. So can you give some comments on the first two questions?
I can. I will preface this by saying I'm not a climate scientist, so I can't talk in too much detail about the balance of CO2 in the atmosphere, other than to say I think it's fair to say we've already upset the balance of CO2 in the atmosphere by putting so much CO2 in the atmosphere that wasn't there 200 years ago. So things like direct air capture are helping us to try and restore the balance. And I don't think we would get to a world where we would over-remove CO2. It is necessary to have CO2 in our atmosphere to a certain degree to make sure that we don't get too cold. But I think that's a problem for 100 years from now. I don't think that's anything to worry about in the foreseeable future. The second question is about ammonia-based capture. There are chilled ammonia-based capture processes that have been developed. Don't hear a whole lot about them as yet. I mean, I'm aware of developments that are underway. They have some advantages and disadvantages. I haven't really touched on them in today's talk because they're really, I mean, they're a variation of the absorption technology, just with a different approach to a solvent. but they are being developed, and the proponents do believe they have advantages for certain applications. And I think that's one of the key things to remember, is that I don't think there's going to be one technology that rules them all. I think we're going to see particular niches that will be dominated by particular technologies. But I think we will see applications where all of these technologies will be deployed in one form or another. So it's a diverse industry. There's a lot of different applications. And we're going to need all these technologies to deal with them.
Okay, thank you very much. And the second set of questions, I would like to combine some of the questions on cost. A few members of the audience asked questions on cost. And Dr. Kerns already provided us with very informative information on the range of cost for CCUS. However, there's one specific questions on the blast furnace gas price range, which is provided as $30 to $40. Has this been proven at commercial scale or demo scale only? And if so, who has been by who?
So those numbers are benchmark study costs. So this was really trying to get apples with apples comparisons of typical costs for different CO2 ranges. As it stands, we don't have a lot of applications in the steel industry. So there's only one steel industry application of capture at the moment at commercial scale, which is the Al Riyadh plant in Abu Dhabi. That's on a DRI unit. So it's a little bit different. It's not blast furnace. It's not blast furnace example. So you should take all of those costs with a grain of salt. You know, the specific costs are going to be very site specific, and they're also going to be capacity specific. You know, the economies of scale are very important. Really, what we were trying to indicate here were the relativities between the typical ranges you might expect to see for different applications. But as always, you know, the devil's in the detail, and I think you need to, you know, investigate more closely for a particular application.
Okay, another questions on cost. How much is the theoretical limit of energy needed to the cost, the kilowatt hour per ton to capture CO2? How much is it affected by CO2 concentration?
I couldn't tell you off the top of my head. I'd have to go and run the numbers on it. You can calculate the thermodynamic minimum amount of energy required, of work required, I should say, in order to separate a gas mixture into CO2 of a certain purity and the rest. That's not really relevant in our sense, because none of our capture plants are anywhere near the theoretical limit. We're miles away from it, and we're probably going to be getting better and better for a long time to come. So that's sort of the thermodynamic minimum, but it is very strongly dominated by the CO2 concentration and the CO2 partial pressure, I should say, in that feed gas. So more concentration, more pressure means that it is easier to separate that CO2 out and requires less energy, both in the thermodynamic minimum case, but it also feeds through to the way actual plants work. So if you're trying to capture from a more concentrated, higher pressure source, so, you know, if I'm thinking here, say, capture CO2 from natural gas that's at high pressure, you know, the partial pressure of the CO2 could be 500 kPa, 1000 kPa, well above atmospheric pressure. The separation is relatively easy and is relatively low cost. Whereas if you take the opposite example where it's really dilute, like direct air capture, it becomes really quite energy intensive. And indeed, that's going to be one of the challenges for direct air capture is they're going to have to be extremely careful to try and use as little energy as possible, recognizing that they do have an energy challenge on their hands. Just the thermodynamics drive that.
Okay, the last questions on cost. The cost of direct air capture is high. What kind of technology innovation, in your opinion, is required to lower the cost of direct air capture?
So there already is being, and we've been having some conversations with both Climeworks and Carbon Engineering on this. Scale is one of them. So economies of scale. So Carbon Engineering has, for example, said that they're specifically designing their standard unit size to be 1 million tonnes a year, because that helped to drive better economies of scale. So in other words, bringing the capital cost down. So even though there's only so much you can do on the energy cost, they could bring the capital cost down by just effectively making everything really big. Beyond that, I think trying to get access to very cheap energy sources. So if you can locate yourself in a part of the world where renewable electricity is cheap. So the Orca project, for example, is located in Iceland, where there's lots of cheap geothermal electricity available. I think that will be another driver. And, if the predictions of the, the growth of renewable energy pan out and we end up with very cheap, abundant renewable electricity, then that will obviously be something that could be, improve the cost base as well. I think there will be technological improvements. I don't know yet which way they're going to go. It's still quite early days for direct air capture, so it's a little hard to make predictions as to which approaches are going to be the most successful. But there's a lot of very clever research that's been going into that, and the costs do seem to be looking like they will come down over time. But how much, I really don't want to try and predict that.
Okay, thank you. Another very technical question. The literature says there is also the cryogenic method, apart from the technologies you mentioned. Can you provide comments on this cryogenic method?
So cryogenic ammonia, for example, was one example that I mentioned before, but I think they're probably talking about, actually chilling the flue gas down directly. It's been under development for quite a long time. Some of the literature goes back, a really long time. I think at the end of the day, it's just proven to not be as cost effective as some of the alternatives. So it's tended to get stuck at the research stage and has struggled to break out of that. That's not to say that it couldn't in the future. I think in particular, if you were to be very careful to integrate that cryogenic operation with, say, an air separation unit in a pre-combustion capture type scenario, you may be able to make it more cost effective, but there's the progress, I think, at the commercial scale has been very limited. But it would be good to see some more, that's for sure.
Okay, thank you. One last question on the technical side. On the degradation of the solvents, the role of contaminants, especially in coal-fired flue gas and NOx, contribute more than just the regeneration cycle. Is that a correct understanding?
We don't install capture plants directly on sort of the gas coming out of the boiler. We make sure that there is gas cleaning in place already. So if it's a retrofit example, the gas that would be taken would be downstream of the existing gas cleaning equipment. So having said that, there is still some residual amount of particulates in there, and they're quite right. So there are systems involved if you've got a particulates issue to filter particulates out of that solvent, which does increase the electricity consumption of the solvent circulation a little bit, because you have to put extra energy in to pump through the filters. But much of the solvent degradation is actual thermal degradation, just based on repeated heating and cooling of that solvent. They just start to slowly chemically break down. Now, some of those degradation mechanisms can be catalyzed by the presence of impurities. That's true. So if you have a very clean gas, it won't break down as fast as a dirtier gas. But really, the challenge is just trying to understand those mechanisms and counteract them, either by changing solvent chemistry, adjusting temperatures. So in other words, don't heat the solvent too much. Try and keep the solvent temperatures more moderate when you're regenerating. But that comes with disadvantages too. If you don't heat the solvent as much, it doesn't release as much CO2 and therefore won't have as much capacity to absorb CO2 the next time it goes around. So it's a balancing act. We're trying to get the best economic performance out of the system, and sometimes the decision is made to accept a certain level of solvent degradation because it's actually cheaper than the alternatives. Now, of course, it's a big area for technological development of trying to get more more solvents out there that are more resistant to degradation, or indeed going for things like potassium carbonate. Potassium carbonate doesn't degrade because it's chemically very simple. It just doesn't have a degradation mechanism. But historically, potassium carbonate just has had much slower rates of mass transfer than amines, which meant that the equipment had to either be physically much larger, or you had to pressurize the flue gas, and pressurizing flue gas is quite an expensive thing to do, because the amount of flue gas you get out of a power station, for example, is very, very large. And if you can avoid pressurizing it, that would be ideal. But there are potassium carbonate based systems out there, including pressurized potassium carbonate, that are effectively saying, well, we'll deal with solvent degradation by using a solvent that doesn't degrade. So it remains to be seen whether they will take a strong place or not. We'll have to wait and see.
Okay, thank you very much. Sorry, this will be the final questions for Dr. Kearns. We received a couple of questions on enhanced oil recovery or enhanced gas recovery. And I understand that EOR, EGR is not exactly related to carbon capture technology, but does GCCI separate EOR, EGR into different category of technologies, or how does GCCI look at EOR, EGR in the context of CCUS?
So I mean, this is at the storage end, so this is not capture. So the capture is happening quite separate and distinct to where the CO2 ends up being stored. Historically, the EOR was one of the main drivers of developing carbon capture processes, because it provided an economic incentive. This is in the days in particular before there was any real focus on greenhouse gas emissions. It was essentially a way to squeeze more oil out of an existing oil field. Some of those operations are still ongoing. The research, as we understand it, suggests that there is a net positive climate impact by putting CO2 into an oil field. The CO2 tends to stay there. And even on balance, accounting for the additional oil production, they are still a carbon. The CO2, the net benefit is that CO2 is still going into the ground. Now, having said that, the EOR is only going to go so far. There's only so many places in the world that require EOR. And for the levels of abatement that we require to go to net zero, we are going to need vast quantities of dedicated geological storage, so saline aquifers or depleted oil and gas fields. So not getting away from EOR, but doing a lot of additional storage that's not EOR related. And I think that's going to be the bulk of the CCS projects going into the future, are going to be dedicated storage.
Okay, thank you very much, Dr. Kearns, for answering so many questions. And thank you to the audience for asking the exciting questions as well. I'd like to hand over to the MC from ERIA so we can move on to the next speaker. Thank you very much, Dr. Kearns.
Thank you.
Thank you very much, Dr. Kearns and Dr. Shinchi for your remarkable technical presentation and discussion. So there are still remaining questions in the Q&A box. So perhaps Dr. Kearns, you may also be able to type the answer in the box.
Okay, thank you for the very thorough lectures by the two experts today. Please give applause to Dr. Kearns from GCCSI and Mr. Kamijo from Mitsubishi Heavy Industries. I would like to give some very brief concluding remarks. I think we learned today quite a lot about various technologies available for carbon capture. And especially Dr. Kearns explained about advantages and disadvantages, and the points to consider, such as the energy source, carbon footprint, and space requirement when considering each technology, as well as the high concentration of CO2 from your point source. And Mr. Kamijo then gave us very good overview of his company's track record in installing the actual carbon capture plants around the world in various sectors. And now we know that carbon capture technology can be applied to many various sectors, but just as Dr. Kearns mentioned, there's still many considerations to be made. regarding, energy source, carbon footprint, the existence of off-taker nearby, etc. I think these are all very useful informations that we can all take back home and use when considering our strategy for carbon capture in the future. I think to conclude, I would like to mention that commissioned by ERIA, Mitsubishi Research Institute is now considering a model case study to look at available technologies, required investment, and the desired legal and policy framework that may be needed to make a successful project case in the ASEAN region. And we would like to share the outcome of this study with the audience in the workshop to be held sometime in the first half of December. The date's not fixed yet, but it will be, when the date is fixed, it will be publicized on ERIA's website. So please, as Dr. Han mentioned at the beginning of this workshop, please come visit ERIA's website from time to time. And also we have 2 remaining technical workshops tomorrow and on Thursday this week. So if you have not already registered, please, I welcome you to register through ERIA's website as well. So this will be the end of my concluding remark. Thank you very much for the 2 lecturers. And also thank you to the audience for participating today. Back to Ms. Diang from ERIA.
Thank you so much for your closing speech and for the insightful presentation before from Ms. Kamijo. So we come to the end of today's workshop. Thank you for the speakers and participants for your insightful presentation and engagement. As Mrs. Shinchi mentioned, that we still have 2 technical workshop series tomorrow and on Wednesday. Please don't miss it. And then if you don't register yet, please register through ERIA website and ASEAN CCUS network website. We are looking forward to see you on the next workshop. And with that, today's workshop is closed. Thank you very much and see you tomorrow.